Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit, I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers. Although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator, the number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers and their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean.
Hi, welcome to this video on rational and irrational numbers. Rational and irrational numbers comprise the real number system. This Venn diagram shows a visual representation of how real numbers are classified. The natural numbers comprise the smallest subset, which is also known as the set of counting numbers. These are all positive, non-decimal values, starting at 1. Whole numbers are the natural numbers plus the value of 0. The integer set of numbers includes whole numbers and all negative, non-decimal values. Rational numbers include all the sets seen here, in addition to the fractional values in between. An easy way to remember this is that the word ratio is in the name of this classification. All numbers included in the rational number set can be written as a ratio of integers. If a and b are integers, rational numbers can be written as a over b, as long as b does not equal 0. Clearly, the set of integers can be written as ratios because any integer divided by 1 results in the original integer. As illustrated here, integers can be expressed as fractions in infinite numbers of ways. The integer 3 can be represented as the fractions 3 over 1, 6 over 2, and even negative 24 over negative 8. The integer negative 5 can be represented as the following fractions. And the integer 0 can be represented as the fractions As a side note, these are not the only fractions that result in these integers. They're just a few of the many examples that exist. Fractions can also be written as decimals. For example, 0.1 is equivalent to 1 over 10 because the 1 is in the tenths decimal place. 0.13 is equivalent to 13/100ths because the 3 is in the hundredths decimal place and the 1 is in the tenths decimal place. .237 is equivalent to 237 over 1,000 because the 7 is in the thousandths decimal place, and so on. These decimals can be written as fractions, so they are considered rational. Other decimals have repeating patterns. These are also considered rational because they can be expressed as a fraction based on the following proof. The repeating decimal 2.17 represents the digits 2.17171717, and so on. So let's try this as a practice problem. Let x equal 2.17 repeating. The repeating decimal is 2 digits long, which represents the hundredths place. So let's multiply both sides of the equation by 100. 100 times x, 2.17 repeating times 100. This results in 100x which is equal to 217.17 repeating. We moved the decimal over 2 spots because we multiplied by 100. Now let's subtract the original equation from this one, meaning minus x and minus 2.17 2.17 repeating. So we have 99x is equal to 215. Notice that the repeating portion of the decimal is now eliminated. Solving for x results in dividing both sides by 99. X is equal to 215 over 99. This is a fractional representation of x equal to 2.17 repeating. This proof shows that repeating decimals are also considered rational because they can be written as a fraction of integers. If you plug this into your calculator, you will get something close to, probably rounded, 2.17 repeating. It is important to note that not all decimals are repeating. Some decimals have an infinite number of non-repeating digits and therefore cannot be expressed as a fraction of integers. These types of real numbers are classified as irrational. While there are an infinite number of irrational numbers in the real number system, most commonly used in mathematics are the square roots of non-perfect squares, like square root of 2, for example, and the constants pi and e. The notation for irrational numbers allows for efficiency in math applications. For geometry, you may recall that pi is equal to about 3.14159 for infinity. This is derived from the circumference of any circle and its diameter. Because the decimal value is non-repeating and infinite, we use an approximate value in math applications. Business applications regarding continuously compounded interest employ the irrational value of e, which has an approximate value of 2.718, again, for infinity.
As you know, there are times when we have to algebraically adjust how a number or an equation appears in order to proceed with our math work. We can use the greatest common factor and the least common multiple to do this. The greatest common factor is the largest number that is a factor of two or more numbers, and the least common multiple is the smallest number that is a multiple of two or more numbers. To see how these concepts are useful, let's look at adding fractions. Before we can add fractions, we have to make sure the denominators are the same by creating an equivalent fraction. In this example, the least common multiple of 3 and 6 must be determined. In other words, what is the smallest number that both 3 and 6 can divide into evenly? With a little thought, we realize that 6 is the least common multiple, because 6 divided by 3 is 2, and 6 divided by 6 is 1. The fraction, 2 over 3, is then adjusted to the equivalent fraction, 4 over 6, by multiplying both the numerator and denominator by 2. Now the two fractions with common denominators can be added for a final value of 5 over 6. In the context of adding or subtracting fractions, the least common multiple is referred to as the least common denominator. In general, you need to determine a number larger than or equal to two or more numbers to find their least common multiple. It's important to note that there is more than one way to determine the least common multiple. One way is to simply list all the multiples of the values in question and select the smallest shared value, as seen here. This illustrates that the least common multiple of 8, 4, and 6 is 24, because it is the smallest number that 8, 4, and 6 can all divide into evenly. Another common method involves the prime factorization of each value. Remember, a prime number is only divisible by 1 in itself. Once the prime factors are determined, list the shared factors once, and then multiply them by the other remaining prime factors. The result is the least common multiple. The least common multiple can also be found by common or repeated division. This method is sometimes considered faster and more efficient than listing multiples and finding prime factors. Here's an example of finding the least common multiple of 3, 6, and 9 using this method. Divide the numbers by the factors of any of the three numbers. 6 has a factor of 2, so let's use 2. 9 and 3 cannot be divided by 2, so we'll just rewrite 9 and 3 here. Repeat this process until all of the numbers are reduced to 1. Then, multiply all of the factors together to get the least common multiple. Now that methods for finding least common multiples have been introduced, we'll need to change our mindset to finding the greatest common factor of 2 or more numbers. We will be identifying a value smaller than or equal to the numbers being considered. In other words, ask yourself, what is the largest value that divides both of these numbers? Understanding this concept is essential for dividing and factoring polynomials. Prime factorization can also be used to determine the greatest common factor. However, rather than multiplying all the prime factors like we did for the least common multiple, we'll multiply only the prime factors that the numbers share. The resulting product is the greatest common factor. Let's wrap up with a couple of true or false review questions. Number 1. The least common multiple of 45 and 60 is 15. The answer is false. The greatest common factor of 45 and 60 is 15, but the least common multiple is 180. Number 2. The least common multiple is a number greater than or equal to the numbers being considered. The answer is true. The least common multiple is greater than or equal to the numbers being considered, while the greatest common factor is equal to or less than the numbers being considered. Thanks for watching. Happy studying.
Now, I know what you're thinking. What does this phrase actually mean? Quite a bit, actually, because that saying provides the key to remembering an important math concept, the order of operations. The order of operations is one of the more critical mathematical concepts you'll learn because it dictates how we calculate problems. It gives us a template so that everyone solves math problems the same way. Let's start off with a simple question. What is an operation? An operation is a mathematical action. Addition, subtraction, multiplication, division, and calculating the root are all examples of a mathematical operation. Let's take a look at this problem. Looks easy, right? Well, it wouldn't be so easy if we didn't understand the order in which the math operation occurs. If we didn't have rules to determine what calculations we should make first, we'd come up with different answers. Should you start by subtracting 4 minus 6 and then multiplying by 7? No. The order of operations tells us how to solve a math problem. And this brings us back to Aunt Sally. Operations have a specific order, and this is what Please Excuse My Dear Aunt Sally helps us to understand. It's an acronym PEMDAS, or PEMDAS, that tells us in which order we should solve a mathematical problem. So first is please, which stands for parentheses. So we solve everything inside of the parentheses first. Then E, excuse, which is for exponents. We solve that after we solve everything in a parentheses. Multiplication, which is the my, and this happens from left to right. And then division, which is the dear, which also happens left to right. And then we have addition and subtraction, which also happens from left to right. And this is Aunt and Sally. Okay, so now that we know the order of operations, let's apply it to our problem that we have here and solve. So let's kind of go down our list. We don't have parentheses and we don't have exponents, but we do have multiplication. So we do that before we do any addition and subtraction. So let's go ahead and multiply 7 times 4. That gives us 28. And now we're subtracting 6, which gives us 22. Now let's look at another problem. Without the operations, you could calculate this as 7 plus 7, which is equal to 14, times 3, which is equal to 42. And this would be wrong. Remember, you multiply before you add. Therefore, the equation should look like this. So when we do problems like this, we can use parentheses to group together our numbers that are going to take place first. So in this case, it's 7 times 3. And when we do that, we get 21, and we have plus 7 left over. When we add those together, we get 28, and that's our answer. Let's look at some more complex problems. The order of operations dictates how to solve this problem. Remember, you multiply exponents first. Here's the wrong way to solve the problem. Why is that wrong? Because you violated the order of operations. You do not multiply first. You perform an operation on the exponent first. This is how it should be done. See, solving the equation in the right order provides the correct answer. Let's try out one more problem. This one is a little bit more challenging, but it perfectly illustrates the order of operations. Remember the order. What do we do first? The number inside the parentheses. So 8 times 6 is equal to 48. Then we subtract 15, and that gives us 33. Here's how the problem looks now. So our next step is multiplication and division. So let's perform all of our multiplication and division problems and then see what we have left. Now we finish with addition and subtraction. So here's what we have. And our answer is 37. There is an exception. If an equation only has one expression, you don't have to follow the order of operations. Here are some examples of single expressions. 10 plus 10. Well, there are no other operations, so you just know to go ahead and add them together and you get 20. Same thing with subtraction, multiplication, or division. All of those are single expressions.
Before we dive in, let's review the basic parts of a fraction. Remember, a fraction simply represents a part of a whole. It has a numerator and a denominator, which tells us what the part is and what the whole is. Let's look at the fraction 3/4 as an example. We can see that the 3 is our numerator and the 4 is our denominator. So the fraction 3/4 is really saying 3 parts out of 4 parts total. It can also be helpful to visualize 3/4 as simply 1/4 plus 1/4 plus 1/4. It is very important to remember that a denominator of 4 does not represent the value of 4. A denominator of 4 represents the value of 1 that is divided up into 4 equal parts, or fourths. The type of fraction we're working with here represents a value less than 1 whole. 3/4 is not quite 1. If we had 4/4, that would be equivalent to 1, but we only have 3 out of 4 parts. We see and use fractions that are less than 1 all the time in our daily lives, whether it's for things like recipes or keeping track of time. Recipes often call for amounts such as 1/2 teaspoon of salt, and we often keep track of time in terms of quarter hours, like a 3:15 for 3:15. Though we observe this type of fraction very frequently in our daily lives, it is not the only type of fraction. Consider the following scenario. You're ordering pizza for a big celebration. There will be lots of hungry guests at this celebration, so you order 3 pizzas. Each pizza is cut into 6 slices. This means that each pizza has 6 equal parts, and as a fraction, 6 would be considered our whole, or our denominator. If your first guest eats 2 slices, we would represent this as the fraction 2/6. 2 parts out of 6 parts total. But what if that first guest was really hungry and grabbed 7 slices? Again, each pizza was cut into 6 equal slices, so 6 remains as our whole, or denominator. But this time our part is 7. In this scenario, our numerator is larger than our denominator, 7/6. Fractions with a numerator larger than their denominator are referred to as improper fractions. Essentially, improper fractions equal a value that is more than 1. 1 whole pizza would be represented by 6/6, or 6/6. 7/6 represents 7/6, which is more than 1 pizza. This could be visualized as 1 over 6 plus 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 1 over 6 equals 7 over 6. It can also be written in another form called a mixed number. An improper fraction and a mixed number will represent the same amount, but simply be written in a different form. For example, the improper fraction 7 over 6 could also be written as the mixed number 1 and 1/6. Mixed numbers and improper fractions share the same amount, but as a mixed number, the parts are collected and consolidated into as many groups of one whole as possible. For example, 4 over 4 would be grouped together as 1. 7 over 7 would also be grouped together as 1. Any value where the numerator is equivalent to the denominator would be expressed simply as 1. In our pizza example, the guest took 7 slices from a group of pizzas that were sliced into sixths. We said this could be represented as the improper fraction 7 over 6, or visualized as 1 over 6 plus 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 1 over 6. As a mixed number, we would group 6 of these sixths in order to form 6 over 6, or 1 whole. By grouping 6 over 6 together, we can see that 1 over 6 is left over. We would write our mixed number as 1 and 1/6. Let's try a few more examples. Let's write the following improper fractions as mixed numbers. 4/3 can be visualized as 1 over 3 plus 1 over 3 plus 1 over 3 plus 1 over 3. We know that 3 over 3 is equal to 1, so let's group 3 of these thirds together. We are now left with 1 and 1/3 as our mixed number. 3/2 can be visualized as 1/2 plus 1/2 plus 1/2. We then know that 2/2, 2 over 2, makes 1 whole, and we're left with 1/2 left over. So 3/2 as a mixed number is 1 and 1/2. Let's try one more example, 7/4. 7/4 is the same as 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4. Now we know that 4/4 are grouped as 1 whole. So these 4/4 pulled over to equal 1, and we're left with 1, 2, 3/4. 7/4 written as a mixed number is 1 and 3/4. This process will take place in reverse in order to convert between a mixed number to an improper fraction. For example, if we started with a mixed number 1 and 3/4 and we wanted to convert it to an equivalent improper fraction, we would take a look at the whole number. In this case, it is 1. This whole number is really representing the denominator that's in the fraction. In this case, it's 4, so the 1 is equal to 4 over 4. When we combine these 4/4 with the 3/4, we end up with 7/4 total, or 7 over 4. Welcome to this video on rates, and more specifically, unit rates. This math concept is practical and useful, so we hope that you come away with a solid understanding and confidence in interpreting the rates that are all around you. Let's get started. Rates are spoken about and used every day in many aspects of life. The concept is pretty straightforward, as rates are nothing more than ratios of values that represent different units of measure. The values that are being compared are called the terms of the rate. Let's consider the treasure trove of rates that may be in your grocery cart the next time you go shopping. In the examples listed here, the rate that you agree to pay is simply the cost related to the quantity of the product. Let's say we have a 12-ounce box of pasta, which costs $1.49. The rate is then $1.49 per 12 ounces. If we have a pound of deli meat and the cost is $9.99, our rate would then be $9.99 per pound. Lastly, let's say we have an 8-pack of 20-ounce bottles of soda and the cost is $5.98. Our rate then is $5.98 per pack. If we look at this last example a little closer, we'll see that there is room to break down the rate even further. The example provides the price of an 8-pack, but what if I want to determine the cost of one 20-ounce bottle? The ratio of $5.98 to 8 bottles provides that information. This quick calculation tells me that each 20-ounce bottle costs approximately 75 cents. This breakdown to determine the cost per bottle may be helpful to determine whether I buy the 8-pack of one type of soda or the individual 20-ounce bottles of another brand on sale for 50 cents each. The process of breaking down the cost to a smaller unit reveals the unit rate of the product. This is helpful to make informed decisions at the store, as the volumes of product in various packaging are often different. By comparing unit rates, savvy customers are able to make price comparisons based on common units of the product, regardless of packaging and advertised sale prices. Let's break down the soda cost per bottle further to determine the cost per ounce. If one 20-ounce bottle costs roughly 75 cents, then dividing that cost by 20 ounces reveals the cost per ounce. So 75 cents per ounce divided by 20 ounces gives you roughly 4 cents per ounce. As you can see, breaking down costs to the smallest unit reveals the cost savings of the sale. Of course, saving a few cents per ounce of soda may not be the deciding factor of your purchase. Other factors come into play when consumers are shopping, like brand loyalty and personal preference. However, comparing unit costs provides an objective way of making consumer choices based on the price. The important thing to remember when analyzing unit rates is that the units must be the same. Let's consider another example to illustrate this point. Suppose you are on a road trip in Wyoming, and on the first day you covered 300 miles in 4 hours of mostly highway driving. You can quickly determine your average rate of speed as miles per hour with the following calculation. Coincidentally, your friend is traveling in Germany, where the standard unit of measure is in kilometers, and she reports that she covered approximately 513 kilometers in 4 hours on her first day of the road trip. Her average speed would be calculated as Clearly, this is comparing apples to oranges in the sense that the underlying units are not the same. A conversion of either miles to kilometers or kilometers to miles must be made to make a fair comparison of average speed. Keep in mind that a kilometer is a shorter unit of distance than a mile. 1 mile is equal to approximately 1.609 kilometers. To convert your average speed of 75 miles per hour to kilometers, simply multiply 75 by 1.609. On the other hand, you could convert your friend's reported kilometers per hour to miles per hour. 1 kilometer is equal to approximately 0.6215 of 1 mile. Multiply this conversion factor by your friend's daily average speed to convert to miles per hour. way that you convert does not matter as long as you compare the average speeds of the same unit. Both conversions show that your friend in Europe traveled at a faster rate on the first day of her trip.
Hi, and welcome to this video on ratios. Ratios are used all the time in many aspects of our lives. In this video, we'll review what ratios represent and how they should be interpreted. As mentioned, ratios are frequently used, but sometimes not fully understood. Simply put, ratios are an efficient way to compare numeric values of different categories. For example, let's say that you have a room of 20 people comprised of 12 women and 8 men. The two categories are men and women, so your ratios would look like this. The ratio of women to men is 12 to 8, and the ratio of men to women is 8 to 12. Note that ratios can be simplified by dividing both values by the common factor of 4, which will not change the meaning of the ratio. The simplified ratio still represents the relationship of the number of women to men, 3 to 2, and the number of men to women, 2 to 3. There are two ways that ratios can be written. This example uses a colon, but you could also use a division bar to form a fraction. 12 over 8 simplifies to 3 over 2. It is very important to note that the order of the categories matters when building a ratio. The first value is technically referred to as the antecedent, and the second value is referred to as the consequent. The antecedent is always compared to the consequent. Interpreting the ratio in context can sometimes be tricky, but becomes easier with practice. Let's look at some examples of ratios you might come across in day-to-day life. Cooking. You are making a batch of your mom's delicious salad dressing. The recipe calls for many ingredients, including 2 cups of extra virgin olive oil and 3 cloves of chopped garlic. In this case, the ratio of oil to cloves is 2 to 3, or 2 over 3. And the ratio of garlic to oil is 3 to 2, or 3 over 2. In cooking, you might hear this referred to as 2 parts oil, 3 parts garlic. This is because the units here are different, cloves versus cups. Shopping. Grocery store displays allow us to compare the value of products based on their unit cost. Many times, this is simply a quick ratio of cost to unit, with a unit being ounce, pound, etc. Suppose you're scanning the cereal aisle and narrow your choice down to your 2 favorites. You decide to be practical and base your decision purely on cost. Both have similar prices, but the volume of the packaging is different. Calculating a quick ratio of cost to unit for each box will reveal the better value. Brand A costs $5.79 and has a volume of 20.35 ounces. Dividing the price by the volume gives us the cost of the cereal per ounce, 28 cents. Brand B costs $6.39 and has a volume of 24.15 ounces. Dividing the price by the volume gives us 26 cents per ounce. Despite being a higher cost per package, choice B is a better value by unit price. This example was fairly straightforward because the volume of the cereal packages were both measured in ounces. Many times, a unit conversion must be made before a unit price can be determined. For example, if we're trying to compare the unit cost of a pound of fresh broccoli to a package of frozen broccoli measured in ounces, we would need to know that 1 pound is equal to 16 ounces before we could calculate the unit cost ratio. In this case, the frozen broccoli would be the better value based on the smaller unit price per ounce.
A linear equation can be expressed in many different ways, but no matter which form you use, it just represents a straight line. The standard form of a linear equation is written as ax plus by equals c, where a, b, and c are constants, and x and y represent variables. This form of the equation is very useful for some purposes in math. For example, a line can be quickly graphed when it is in this form by finding the x and y intercepts. There are also methods of solving systems of equations that require each equation in the system to be written in this form. Rearranging the standard form equation into slope-intercept form, y equals mx plus b, reveals other key features of the line, namely the slope and the y-intercept. The slope of a line describes the slant, or steepness, and the y-intercept is the point on the graph where the line crosses the y-axis. Notationally, slope is represented by m and the y-intercept is represented by b. Because the y-intercept is an actual point on the coordinate plane, it is represented as an ordered pair, 0b. Sometimes you will be asked to rearrange an equation from one form to another. Here's an example. 2x plus 3y equals 12. Remember, the standard form of a linear equation is ax plus by equals c. So this is currently in standard form. If we want to change it to slope-intercept form, we are going to need to rearrange it so that y is by itself on our left side. Our first step is to subtract 2x from both sides. 3y equals 12 minus 2x is what we have now. Then we're going to divide everything by 3, which gives us y equals 4 minus 2/3 x. This is almost right, but if we look again at slope-intercept form, we see that we need the x term to be in front. Thankfully, we can think of this as 4 plus negative 2/3 x and use the commutative property of addition to swap their places. This gives us y equals negative 2/3 x plus 4. The resulting equation is more informative about the line than the original equation in standard form. The coefficient of x, negative 2/3, is the slope. A negative slope tells us that the line slants downward from left to right. The y-intercept of 4 tells us that the line crosses the y-axis at the point 0, 4. Now that we have seen how to convert a standard form equation into slope-intercept form, let's practice recognizing the key features of slope and the y-intercept with a few examples. For these examples, we want to name the slope, describe the slant of the line, and name the y-intercept as an ordered pair. Y equals 2x plus 3. The slope of this equation is m equals 2, the coefficient of the x variable. A positive slope indicates that the line slants upward from left to right. The y-intercept is b equals 3, which indicates that the line crosses the y-axis at the point 0, 3. Let's try another one. Y equals 3/5 x minus 2/3. The slope of this equation is m equals 3/5. Because the slope is positive, the line slants upward from left to right. The y-intercept is negative 2/3, which indicates that the line crosses the y-axis at the point 0, negative 2/3. Let's try one more. Y equals negative 5x minus 2. The slope is m equals negative 5. Negative slope means that the line slants downward from left to right. The line crosses the y-axis at the point 0, negative 2. As you can imagine, knowing where the line crosses the y-axis and the slope of the line will make the line very easy to graph. Now let's take a look at how slope provides you with instructions to graph from the y-intercept. Any value of slope can be looked at as a fraction, where the numerator indicates where to move along the y-axis and the denominator indicates where to move along the x-axis. Movement along the y-axis is typically referred to as the rise. A positive rise value would instruct a move up the y-axis, while a negative rise would indicate a move down the y-axis. Likewise, a positive run value would mean a shift to the right, and a negative run would mean a shift to the left. Here are a few examples to practice identifying the rise and run indicated by a given slope. M equals 5. This slope is not written as a fraction, but any whole number can be rewritten as a fraction over 1. M equals 5 over 1. The numerator, 5, is the rise. The positive value means up 5. The denominator is the run. Positive value means right 1. Let's try another one. M equals negative 2/3. When you have a negative slope, you can consider either the numerator or the denominator to be negative, not both. For this example, let's consider the numerator, the rise, to be the negative value. Negative value means down 2. The denominator, 3, is the run. Positive value means right 3. Here's one last example. M equals negative 3. First, we need to rewrite the whole number as a fraction, negative 3 over 1. Let the numerator be the negative value. Rise is negative 3, down 3. Run is 1, right 1. Now on to some graphing. People sometimes find it helpful to use the notation of slope-intercept form to get started. Begin at B and move according to M. Let's graph the linear equation in slope-intercept form. Y equals 2/3 x minus 2. Step 1. Begin at B. Plot the y-intercept 0, -2, first point. Step 2. Move by m equals 2/3. Rise equals up 2. Run equals right 3. Plot the second point at 3, 0. Step 3. Repeat the rise equals up 2 and run equals right 3. Plot the third point at 6, 2. Step 4. Draw a straight line through the 3 points. Got the hang of it? Let's try one more. Y equals -2x minus 3. Step 1. Begin at B. Plot the y-intercept 0, -3, first point. Step 2. Move by m equals -2 over 1. Let the rise be negative. Rise equals down 2. Run equals right 1. Plot the second point at 1, -5. Step 3. Repeat the rise equals down 2 and run equals right 1. Plot the third point at 2, -7. Step 4. Draw a straight line through the 3 points. Note the slant downward from left to right due to the negative slope in this equation. Now that we have had some review of the key features of linear equations, we have the tools to explore the point-slope form. This form is of special use if we know one point that is on the line and the slope. The general form of this arrangement is y minus y1 equals m times x minus x1, where m equals the slope and x1, y1 is another point that is known on the line. Using this template, let's practice identifying the slope and the point from the following examples of point-slope form. Y minus 5 equals 3 times x minus 2. This is a straightforward example. First, identify the slope as the coefficient outside the parentheses, m equals 3. When naming the point on the line, note that in the general form, the x-coordinate is being subtracted from x, and the y-coordinate is being subtracted from y. So the ordered pair of the point will be 2, 5. Here's another one. Y plus 3 equals -1/2 times x minus 4. The slope in this equation is m equals -1/2. How is this equation different from the general form y minus y1 equals m times x minus x1? You may have noticed that the y value of the point 3 is being added. To identify the point that is on this line, the equation must look like the general form, which subtracts the coordinates of the point. Therefore, the point can be seen more clearly if the equation is written as y minus -3 equals -1/2 times x minus 4. Subtracting a negative value is the same as addition. Now we can see that this line travels through the point 4, -3 and has a slope of m equals -1/2. Let's look at one more example. Y plus 12 equals -3 times x plus 5. By now, you can quickly see that the slope of this equation is m equals -3. This equation also does not match the general form, but it can be rewritten as follows. Y minus -12 equals -3 times x minus -5. This adjustment reveals that the point that is on the line is -5, -12. Once you feel comfortable with identifying the slope and the point from this form, you can graph the line as we did before. Y minus 5 equals 1/2 times x minus 2. Step 1, identify the slope m equals 1/2. Step 2, identify the point on the line 2, 5. Some students find it helpful to switch the sign of the given formula to determine the coordinates of the point. Step 3, plot the point 2, 5 as the first point. Step 4, move by m equals 1/2. Rise equals up 1, run equals right 2. Plot the second point at 4, 6. Step 5, repeat the rise equals up 1 and run equals right 2. Plot the third point at 6, 7. Step 6, draw a straight line through the 3 points. Alright, we've covered a lot of ground in this video regarding the different ways linear equations can be written. While the structure of the equations looks different, they all represent a line. The use of each depends on what you are given or what you are asked to do. That's all for this review. Thanks for watching and happy studying.